Unidentified anomalous phenomena, UAPs for short, are the new UFOs, and a new sighting just dropped. In the past decade, we've seen more and more of those, anomalous incidents. It's not that the incidents themselves are new, it's just that now we actually hear of them. Indeed, just a few months ago, I talked about a group of astrophysicists who found evidence for UAPs in old telescope images. This finding has now been confirmed by an independent analysis. Still, scientists are afraid that research like this will ruin their career, as a series of new interviews shows. Let's have a look. In the paper that we talked about in October, scientists analyzed old photographic plates. They found multiple incidents of transients that are objects which appear and then disappear in a short time. This means the objects must have moved fast and were nearby. Some of the objects appear in configurations like in a straight line. The researchers found more of those transients in photos taken in the Earth's shadow, which suggests that the objects reflect light. This light reflection requires reasonably even surfaces and isn't compatible with natural objects like maybe asteroids. Asteroids are many things, but well-polished isn't one of them. Most intriguing, the images all date to before the time that we had the first satellites in orbit. No one has any idea what these images show. The author of the new paper now did a similar analysis with a different set of photographic plates, and to make a long story short, he found the same thing. There are things, UAPs, appearing in the plates and then disappearing. He found 35 such cases. They appear to be quite close to Earth at a time when we didn't have satellites in orbit. The first reports from October were published in two peer-reviewed papers, but the archive, the preprint server that's widely used in physics, refused to publish them. The new paper now did appear on the archive, rather confusingly, because this one hasn't been peer-reviewed. This makes me think the archive moderation is more disorganized than evil, but either way, it's unfortunate because it certainly discourages scientists from studying these phenomena. And I really want to know what they are. The problem is that the way things stand, there are few scientists who dare to study UAPs, which leaves the field over to, less scientifically minded people who then sit in the US Congress and talk about multidimensional beings. And there is evidence of puzzling unresolved cases, like this one, which is from 2013, when an unknown object flew across an airport in Puerto Rico and was captured by an infrared camera. The object then enters the ocean. A group of scientists looked at the footage and reported the object splits into two parts shortly after entering the ocean and then briefly re-emerging. Frame-by-frame analysis ruled out the possibility of a reflection or of a second object emerging from the water. So what was it? And then there are these videos released by the Pentagon. What are they? We could certainly need more scientists looking into this. The problem is that scientists who want to work on UAPs are afraid to damage their reputation, and there are no funding sources for this sort of research either. A sociologist just published a paper with interviews of 21 researchers, and the running thread is that they're just afraid to work on it. Several report that they waited until they had tenure, so a secure position, and one of them bluntly says, the stigma is still a real thing, especially in a world where science is already horribly underfunded. The thing is that if now you start being known as a cuckoo, you're going to stop getting funding. It's not that they're not interested, they just don't dare look at the matter. One of those scientists explains, so you have to understand a lot of people would not admit that they're interested in it just because they worry about their image. I mean, they're basically asking themselves, what do other people think and how would I be viewed? And that's the way that Neil deGrasse Tyson will respond to it. That's the way that Brian Keating will respond to it. That's the way many others will respond. And the problem with that approach is that you're trying to get as many likes as possible. AL. Can't think of any astrophysicist who's interested in aliens with those initials. None at all. I think the problem's much simpler. Tyson and Keating and I and many others don't talk about UAPs, or at least not often. because there's very little to talk about. I mean, I can't stand here and say, hey, there's a video and I have no idea what I'm looking at, but so what? 99% of the videos on YouTube, I don't know what I'm looking at either. So it's somewhat of a chicken and egg problem. The field has a stigma because there's so little research, and because there's so little research, it's got a stigma. But things are changing. As you can see, there are now scientists who seriously look into these matters. And since 10 years something I no longer need to worry about, I can promise to keep you well informed, so don't forget to subscribe. The Riemann hypothesis is one of the most famous open problems in mathematics. But it doesn't just haunt mathematicians, because the implications of the hypothesis, if they are ever proved, would be so profound. Physicists are trying to solve it too. Indeed, in the past years, it's turned out that the Riemann hypothesis might be related to black hole physics and, ultimately, quantum gravity. The Riemann hypothesis has been open for more than 160 years, and if you solve it, you can win $1 million prize, enough to buy a truly irresponsible amount of cheese. At the face of it, the Riemann hypothesis sounds like a hopelessly abstract problem that no one could possibly care about. It's all about prime numbers. If you look at the sequence of primes, 2, 3, 5, 7, 11, 13, and so on, they look irregular. There is no obvious pattern. But in the 19th century, Bernhard Riemann discovered that the distribution of primes is connected to a function called the zeta function, which can either be written as a sum over all integers or as a product over the primes. So this function links all the integers and the primes. What makes the zeta function so important are points where the function becomes zero. The exact positions of these zeros determines the distribution of the prime numbers. The Riemann hypothesis now says that all the important zeros lie on a single vertical line in the complex plane. If that's true, then the primes are distributed as regularly as they possibly can be. Trust the Germans to come up with orderly rules even for prime numbers. Yes, it's rather obscure mathematics, but in the 1970s, physics entered the chat, and that changed the story. Normal people think of what happens in nature in terms of things that have positions and move around. Physicists like to think of what happens in terms of energy. Why? Because that works both for quantum and non-quantum physics. Think, for example, of the electrons around atomic nuclei. Speaking of their position makes no sense. Speaking of their energy does make sense. And physicists discovered that there are chaotic quantum systems whose energy levels look almost like the distribution of the zeros of the Riemann function. So, wow, now we have quantum physics and chaos and something with the Riemann hypothesis combined. Almost. Ever since then, physicists have looked for an example where the match is not almost, but exact. Then, proving the Riemann hypothesis would come down to analyzing the quantum behavior of a physical system, and who wouldn't want that $1 million? There is a new attempt at this every few months, for example, this recent paper. And this is where the new work comes in. It's a continuation of earlier work that looked at the behavior of gravity very close to a space-time singularity. In general relativity, when you approach certain singularities, the geometry can become extremely chaotic. In the case that the authors looked at, the complicated gravitational equations simplify in an unexpected way. The dynamics begins to resemble a sort of quantum chaos, and lo and behold, its energy properties can be written as a product over prime numbers. Physicists call this a Riemann gas. The idea isn't entirely new, but what's new is that this appears in a black hole. Now, to be clear, this function that they get is similar to the Riemann zeta, but not exactly the same, and the type of black hole that they considered is not an astrophysically realistic one. So, Why am I telling you about this? It's because this is an example of a trend that's been going on in the foundations of physics for a decade or two since string theory peaked and entered its decline. Physicists are looking for new mathematical links that could help them combine gravity with quantum physics. And one of the ways to do this is to stop talking about what happens in space and time and instead ask what happens to energies. This could work for the same reason it worked for quantum physics originally. Energy is the link between quantum and non-quantum physics. I give this paper a 7 out of 10 on the bullshit meter. Why is it so high? It's because I rate papers for their relevance in the field. And while I think the maths is fine, in this case the physical relevance is extremely unclear. It makes me somewhat afraid that rather than progressing the foundations of physics, we might see yet another wave of abstract maths that will eventually lead nowhere. Then again, I'm personally quite intrigued by these deep links between the Riemann hypothesis, chaos theory, black holes, and somewhere there are also quasi-crystals in there. And I totally want to see more research on this. Okay, I really just want to see physicists solve the Riemann hypothesis before mathematicians get there. Supercomputers are now good enough to simulate a full human brain. That sounds like science fiction, but that's what scientists showed in a recent paper. Haven't we tried this before and it didn't work? Kind of, but this time it's different. Computers have much advanced, and the scientists have come up with better ways to calculate what human brains do. How? And even if we could simulate a human brain, should we? Let's have a look. The current models for artificial intelligence use computer code to simulate neural networks, which are motivated by the functions of neurons in real brains. But these AIs are far from the real thing. The biggest difference may be that real brains are extremely differentiated in function. They have areas for different tasks. Scientists have tried to reproduce the function of real neural nets on a computer for decades. They started with a small worm whose brain has just about 300 neurons. The first simulations could reproduce simple movements of the worm. By 2023, science and technology had advanced enough to fully simulate the brain of a fruit fly with about 140,000 neurons. The Allen Institute for Brain Science, meanwhile, has been working on putting a mouse brain on a supercomputer. The entire mouse brain has something like 70 million neurons. They are now at a few million, and that runs on a supercomputer in Japan. The new paper now outlines a new method that'd be a big and sudden jump forward, almost reaching the capacity to simulate the human brain. The human brain has about 80 billion neurons. In the paper, they write that with their new method, network sizes of 2 × 10⁻⁻⁻ neurons can be reached with our approach on the upcoming exascale supercomputer Jupiter. So that'll be 20 billion neurons with the next upcoming supercomputer. It's fair to expect then that the next generation of supercomputers will be able to simulate the entire human brain. What is this new method? Basically, they have removed a bottleneck in the way that big neural networks are currently simulated. With the previous method, one would instantiate the entire network on the entire computing cluster. With the new method, they say we give some 100,000 neurons to each GPU, let each GPU deal with those, and then connect the GPUs. That is, this is a massively parallel and local approach that avoids a lot of shoveling around of information, so it's computationally much leaner. The maths is then pretty straightforward. In detail, they estimate that a single NVIDIA A100 GPU could deal with about 225,000 neurons. The Leonardo supercomputer in Italy has about 14,000 GPUs, so that'd make about a few billion neurons. Jupiter is a new supercomputer cluster currently under development in Jülich in Germany. Each GPU could manage 800,000 or so neurons and a total of 20 billion. That seems big, but wait, wasn't there a similar project a decade ago? Yes, there was the Human Brain Project, an international effort but centered in the EU. It ran from 2013 to 2023, had over €1 billion in funding and aimed to build a digital human brain too. They wanted to simulate a few million neurons, but it was a disaster. The project leadership had this great ambition of simulating parts of the brain, but it was somewhat unclear what this would be good for. Neuroscientists wanted to study more specific details of processes in certain parts of the brain. That led to a quite big rift in the community, and in the end, to make a long story short, not much came out of it, besides a lot of reports. Some of the authors of the new paper also worked on software for the previous Human Brain Project. So what's different this time? In a nutshell, more neurons, fewer neuroscientists. I think these people just want to simulate a human brain to see what it does. They don't have any particular plan for what to do with it. And I can totally see the point of doing this. What could such a simulation do for us? I don't know, but we can talk about some things it wouldn't do. We actually don't have the exact map of any human neural network that's called the connectome. So we can't build an entire human brain because we don't know exactly what it looks like. Without doing that first, a computer simulation could at best be a guess for how the brain is connected, and it's somewhat unclear how much it could do. Another issue is that it'd be difficult to train such an artificial human brain because we'd first have to figure out how to convert input into neural signals. We know some of that, but only in rough terms. And then there is the moral question. Should we simulate a human brain? What if it does actually think? What if it suffers? What if the EU Commission says we're not allowed to turn it off and it blocks the only German supercomputer cluster? Personally, I think it'd well be worth it. It'd demonstrate that there's at least one functioning brain in Europe. Thanks for watching. See you tomorrow.